Good morning, afternoon, or evening, class. This is Mr. Ireland again. Hope you are feeling great. Hope you're staying away from large crowds and just overall in good health right now. So we're going to move on to our second day of chapter 10.6. And the focus today is going to be to use segments of tangents and secants to find missing variables in circles. So let's go ahead and get started. So before we begin, I need to clarify to you what a tangent segment is, a secant segment, and an external segment. So we did learn that secants were figures that it was a line that crossed through a circle into places. So there goes a secant line right there. Now, we oftentimes will talk about just what's called a secant segment. So let me go ahead and read that definition for you. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. So as you can see right over here, this is what we would call a secant segment. Now, we've talked about tangents before, and we've said tangents can be lines, tangents can be segments, and they can be rays as well. So that is not too much of a difference, but the secant segment is something you've never heard of. Now, we also have an external segment, which is part of that secant segment. So by that, we're referring to this portion right here. It's drawn in red on the side, but I'm just going to color over it in purple. That is the external segment of that entire secant segment. So now that you have some of these terms down, we're going to go ahead and take a look at a theorem. But before that, we're going to check out this website, MathOpenRef, and I want to show you a property that these secant segments have. So right here on MathOpenRef, I will go ahead and provide the link. You'll notice as I move these secant segments around, just pay close attention to the numbers, you're going to notice that the external portion right here, PA, is 18.2, that the external multiplied by the entire secant segment, P to B, which is 33, has a product of 644. Now, if you look at the other secant segment, and you look at just the external portion, PC, and you multiply that by PD, which is the entire secant segment, that product is also equal to 644. And that happens however these secant segments are moved around. So I can move this a lot of different ways. And you're going to notice that that product never changes. And I believe I can move this and change the size of this. I can't do that. What? Hopefully you guys can see that point and that property. And that brings us here to the segments of secants theorem. So I am going to give you the simplified version that is color-coded. And if you want to read it, it's in your textbook. Here it says if two secant segments share the same endpoint outside of a circle, then AB, which is a part in orange, times the entire secant segment. So let me just highlight that. So AC refers to the entire segment, is equal to AE, which is the external portion of the other secant segment, times the entire secant segment AD. So another way to think of it is kind of like outer times whole, outer times whole. All right, and we're going to go ahead and practice that on the upcoming examples. All right, so on these examples here, let's start with 3A. We have two secant segments. So we've got 9 out here. So we're going to go outer times whole. 9 times 9 plus 11. And that's equal to 10 times 10 plus x. All right, that's going to simplify to, 9 times 20. This side we're going to have to distribute. That gives us 100 plus 10x. 180 equals 100 plus 10x. Subtract 100 from each side, giving us 80 equal to 10x. When you divide both sides by 10, you will end up with a solution of 8. X is equal to 8. Now, moving on to 3b. So I'm going to go ahead and erase all the work on this side. So go ahead and pause it if you need to refer back to it. But I'm going to erase that because I need all the room I can get for part 3b. This one takes a little bit longer because it does involve some factoring. So here, I'm going to take, I'm going to take the outer I'm sorry guys, just trying to figure this thing out here. Okay, so I'm going to take the outer value, which is x, and I'm going to multiply by the whole thing, which is x plus 2. I'm going to take the outer, which is 5, and I'm going to multiply that by 5 plus 11. Now when we distribute on this side, we're going to get x squared plus 2x is equal to 5 times 16, which is x squared plus 2x equal to 80. So remember, you have multiple exponents here. You've got a square power, exponent of variable squared, variable to the first power, and then a constant. You're going to have to move the 80 over to the left side, or whatever side you choose. Here it's easier to move the 80 over to the left, and we have our trinomial that we're going to want to factor. So we talked about yesterday was this little x factor problem here. So we're looking for two numbers that multiply to make negative 80 and add to give 2. Now, through the process of trial and error, you will hopefully figure out that 10 times negative 8 is the best choice. Because 10 times negative 8 is negative 80, and 10 plus negative 8 is 2. So now, we're able to factor this down to x plus 10 and x minus 8. And that's going to give you two solutions. The first solution is negative 10. Second solution is 8. As we talked about yesterday, you can't have negative length, so we're going to go ahead and cross that one out. And our solution is 8 for this problem. All right, so please pause the video for a moment and try these two problems out, and I will reveal the solution after you're done. All right, so hopefully you did pause the video. If you did not, let's take a look at the solutions here. So for number 1, notice I took the value of 6 outer times whole. That's what you see on this side. And then on the right side, outer times whole. That's this portion. You have to distribute to get 25 plus 5x. And then use a little bit of algebra here. Subtract 25 to both sides. Divide both sides by 5. And down here, not sure if you guys can see that, but you get an answer of 13. All right, problem number 2. We've got the outer times the whole, x times x plus 3, which does involve some distributing. And then you've got 4 times the whole, 4 times 4 plus 6, which is basically 4 times 10. That gives us 40. All right, so here, now we're going to have to move the 40 over to the other side. And you get x squared plus 3x minus 40 equals 0. Now, if you wrote this portion on the right side, you're going to want to move all the terms to the right side and make sure 0 is by itself on the left side of your equation. Just make sure you get all these 3 terms by themselves on one side of the equation, whether it's the left or the right. All right, now did some factoring here. Negative 40 on the top, 3 on the bottom. 8 times negative 5 would be our solution. As you can see here, it gives us our factored form. And now you set each factor to 0, like we talked about yesterday. X plus 8 equals 0. X minus 5 equals 0. And when you solve for those equations, you get negative 8 or 5. And as we discussed, you may not have a negative length in geometry. So we're going to go ahead and just stick with our answer of 5. All right, so we're going to speed up here because we need to get through one last theorem. And for this problem, we are going to use the segments of secants and tangents theorem. So you're going to notice on this problem that we have a tangent. We have a tangent segment right here. I need to get myself a better stylus. I'm really sorry, everyone. This is not very great, but making the best of what we have here. Here's our tangent segment. And then you have your secant segment over here. So you've got tangent, secant in this scenario. All right, and notice the colors here, and notice that now you're going to square this outside tangent term. Notice you have EA squared. So that tangent portion gets squared, and this secant follows the same rule where you take your outer or your external, outer, and then you multiply it by this whole here. All right, so I have a 15-minute time limit, so I'm going to speed this up and we're going to try some problems out here. All right, example number 1A here. So I'm going to take this tangent portion. This is my tangent. And I'm going to square that. I'm going to write x squared. And that's going to be equal to my secant portion, 12, times 12 plus 15. That's going to give us x squared is equal to 12 times 27, which simplifies to x squared equal to 324. When I take the square root of each side, I put my plus minus. We're going to get an answer of x is equal to plus or minus 18. And remember, the negative solution doesn't apply in geometry, so we're only worried about the 18. Don't worry about that negative right there, positive 18. All right, on the next example here, I'm going to take my tangent portion and write 7 squared. And then I'm going to take my secant portion. That's equal to 5 times 5 plus x. Now simplifying this is going to give us 49 is equal to 25 plus 5x. Subtracting 25 from both sides gives us 24 equal to 5x. And dividing both sides by 5 will give us a decimal answer of 4.8. All right, so pause the video right here and try these out, and we'll check back in a little bit to see how you did. All right, so hopefully you did pause the video. Let's go over these solutions because I have about 1 minute left here. So I'm going to take this tangent portion. That's where you see the squared part at. Your secant portion, 1 times 1 plus 3. That's this portion here, and you get 4 equals x squared. Now you've got a square root each side, and here you have a plus or minus 4. Remember, in geometry, we don't worry about that negative length, so our answer is just 2. All right, problem number 2, same thing. I just wanted to mention before we run out of time that you do have to do some factoring here. Negative 144, and it's going to be 18 times negative 8.